Greetings, Panthers. Dr. Augustine. I hope you guys are doing well today. Today we are going to take a look at the concept of atomic mass, and that's this number on an element on the periodic table. Now, I'm going to apologize for this carbon symbol. It looked a lot nicer on my computer screen than when I exported it. For some reason, it put these lines in there. So, apologize for that right off the bat. This video covers chapters 2.8, Intro, Atomic Mass, the average mass of an element's atoms. And we're going to answer a couple of questions here. Why is the mass number not a whole number? So this number is a whole number, and if you recall from one of our earlier videos, this quantity is called the atomic number. Remember, that atomic number tells us how many protons we have in our atom, and that's the unique thing that makes, carbon carbon is it has 6 protons. But then we have this other number, which shows up on a lot of periodic tables, and that is called the atomic mass. So we're going to find out the origin of this number, and you'll notice on the periodic table that none of those numbers are whole numbers. These are always whole numbers. These are not whole numbers. So we're going to find out where that comes from. And we're going to answer another question. Can we find a carbon atom that has a mass of 12.0107 AMUs, atomic mass numbers, in nature? So that's this number here on the periodic table. Can we find an atom out in nature that has a mass of 12.0107? And I'll save you watching the whole video. The answer is no. There is no element out in nature that has a mass of 12.0107, which might make you ask the question, well, why the heck is this thing on the periodic table? So that gets us into the topic of relative isotopic abundance and the atomic mass, which is actually a weighted average of all the masses of the different isotopes. So we're going to talk about that in just a couple of minutes. First, I want to point out how these sorts of measurements were done. So we don't have a balance in our lab that we can just walk into lab and measure an atom. They're extremely small, extremely light, but we are getting close. We're getting much better in terms of the capability of looking at things on the atomic scale. So we've got two major instruments which allow us to look at the masses and look at individual atoms. The first one is called a scanning tunneling microscope. That's what this STM stands for. So scanning tunneling microscope is an instrument that has a sharp tip that's typically made out of some metal, so it's a conductive surface, and you have another surface that you're interested in looking at. And if you bring this tip close enough to the surface, but not actually touching the surface, you can get electrons to jump from the tip to the surface or from the surface to the tip, depending on how you're doing the experiment. And this electron jumping is a flow of electrons, which is a current, and we can measure those currents. They're very small currents. We can measure those currents. That's called a tunneling current. And you have to take physics, modern physics, to understand the nature of tunneling. It's a quantum mechanical phenomena. But basically the idea is you can scan the tip back and forth across the surface, and what's shown here is a flat surface here with a 1 atom bump next to it, and we have a tunneling current, and the tunneling current is extremely sensitive to height. So that 1 atom difference, which is only fractions, tenths of a nanometer tall, will change the tunneling current by 1 or 2 orders of magnitude. Huge increase in the tunneling current by going over 1 bump. So what you can do is you can actually map out the surfaces, and this is the HERO experiment that Don Eigler from IBM Research did, going on about 20 years ago now. And 2 different surfaces. This is a copper surface with 2 defects on the surface of some sort. I don't know what those defects are, but I like this picture because it's really a beautiful picture. It looks like 2 stones were thrown in the water at the exact same time, and there's ripples going out from those stones. And then where the 2 ripples interact with each other, we get blue spots and red spots, which correspond to different tunneling current. So this is exactly analogous to taking 2 stones and tossing them in the water and watching the waves generate away from where the stones hit. And these ripples are due to what's called constructive interference, and these are actually the waves of electrons around these defects, and you get interference of these electrons waves with one another to form this beautiful constructive interference pattern. Here's another one. This is actually probably the most famous image from Dr. Eigler's group. And this is a copper surface with 48 iron atoms that have been arranged. And this was not like, wow, they just got lucky. They were scanning around and found these 48 atoms in a perfect ring. No, what they did was they used this tip actually to pick up an iron atom and move it into place and put it in exactly in this ring. So there's actually an extra iron atom there, there's an extra iron atom there. We've got 48 atoms arranged in a perfect ring. And the other crazy thing or beautiful thing about this is you get, again, it looks like a wave pattern inside of here. And these are electrons stuck inside of this ring. So the electrons would normally, or they're called free electrons in a metal, so they normally would be able to move across the surface, but they run into this wall, which are these iron atoms, and they bounce back, and you end up getting this beautiful standing wave pattern. That little bump there in the middle is actually not an iron atom. That's due to the standing wave of the electrons. If you ever wondered, what is an electron? Well, one of the ways we can describe it is with wave properties, and here's a picture of those wave properties. Here's a little less incredible image. I mean, these you can actually look at, and a lot of textbooks have used this image to show, first of all, to show the principle of STM, but also to show the idea of electron waves. This one's a little less amazing. This is from my lab, and these are copper atoms on what's called highly oriented pyrolytic graphite. So it's a piece of graphite, but it's not the kind you get in a pencil lead. It's a little more expensive version than that. It comes in these sheets. And if you peel the sheets off very carefully and then you do STM on it, you end up with these bumps on the surface, and the bright spots are the atoms and the dark spots are in between. And so this picture right here is 12 carbon atoms wide down by 12 carbon atoms long. If you look at the scale really carefully, these are in nanometers, so that's 0 to 1 nanometer on both axes. And so incredibly, you can see around 144 carbon atoms on this image using scanning tunneling microscopy. So this is a relatively new technique. It was invented in 1982. It became much more sort of commercialized in like 1990, so it hasn't been around all that long. But now we can actually look at individual atoms or defects on surfaces using this technique called scanning tunneling microscopy. And then we already talked about this a couple of videos ago, but we can use mass spectrometry to figure out the different masses. So remember the way that works. You introduce a sample, a gaseous sample, into a vacuum chamber. You have some way of ionizing the gas, remember creating an ion. It goes through some electric field, goes around a magnetic field, and then gets separated out by mass to charge ratio. And what's really amazing about mass spectrometry, not only do you get the masses of the atoms, it is actually sensitive enough to measure the difference between two isotopes. Here's an example of chlorine-35 and chlorine-37. And you can see we get a bigger peak for chlorine-35, which tells us that chlorine-35 is actually more abundant around the Earth than chlorine-37 is. There's less chlorine-37 compared to the amount of chlorine-35. So this ratio is called the relative abundance. And if you were to go all around the world and measure chlorine atoms all around the world with an instrument like a mass spectrometer, and then took the average of them, the relative abundance is the average percentage of each element on the periodic table averaged out around the world. Now, if you really want to get picky about it, it's not a perfectly even number. It depends a little bit on the conditions that it was under. But for first order approximation, we can say that no matter where you are on Earth, the fraction or the relative abundance of different isotopes is going to be constant around the globe. So we can use these numbers then. We can set up a ratio between these numbers to find out how much chlorine-35 there is compared to how much chlorine-37 there is. So when they actually do this measurement, they typically set the highest peak to 100%, and the lower peak is whatever relative. If you look at that, that's like, 30 or something like that. And they just set up a ratio between those two things. And it turns out that for chlorine-35, the percentage is 75.78%. And for chlorine-37, it is 24.22%. Now, of course, it is not important for you to memorize what these percentages is for every element on the periodic table. The important thing to note is that every element on the periodic table has potentially several different isotopes. Now, this example has 2, but some elements have 3, some have 4. So it just depends on what the element is that you're looking at. So if you think about the history of these numbers and where they came from, you might be thinking to yourself, well, look, the STM was only invented in 1982, and mass spectrometers weren't invented much long before that. But we've had these numbers on the periodic table for a long time. So where do these numbers come from? And the answer to that question is, when they first started developing these numbers, no one had an instrument to measure the mass of an individual atom. It wasn't until the invention of things like mass spectrometers and scanning tunneling microscopes, particularly mass spectrometers, were they able to really carefully measure the masses of each individual atom and specifically even isotopes. So the way they did it was a pretty clever way. They decided to make element masses relative to one another. And the standard they chose was carbon-12. It's a very abundant element, it's common in nature, it's easy to obtain. So carbon-12 is the basis for the entire periodic table. All the masses on the periodic table are based on carbon-12. Now what do we know about carbon-12? We know that carbon has 6 protons, and we know that from over here. And we also know, because it's carbon-12, that it also has 6 neutrons. So carbon-12, if we have an atom of carbon-12, we know that it's going to have 6 protons and 6 neutrons. So that was assigned an arbitrary mass. And the mass for carbon-12 was assigned to be 12.000 all the way out to infinity atomic mass units. That's what this AMU means. So 12.000 atomic mass units was defined to be the mass of a single carbon atom. Okay, why is that useful? The reason why that's useful is then you can take other elements on the periodic table and you can compare them or make a ratio between them and other elements on the periodic table. So it turns out that hydrogen has a mass that is 8.4% of carbon-12. So if we took a carbon-12 atom and we were to compare that to the mass of helium, it's only 8% of the mass, or 8.4% of the mass of carbon-12. So what does that mean? Well, if I take 8.4% and I convert that into a decimal form, which would be 0.08400, if I take that number, 0.08400, and multiply that times 12.000 all the way out to infinity, this is AMUs, or my units, that equals to 1.008 AMUs. So the mass of one hydrogen atom is 1.008 AMUs because it's been determined that the mass of a hydrogen atom is only 8.4% of the mass of a carbon atom. Likewise, if we did the same thing for all the other elements, we would end up with things like oxygen is 16.00 AMUs, that's one oxygen atom. One iron atom is 55.85 AMUs, etc. So what we end up with is all these numbers on the periodic table. There's my carbon, 12.01. There's iron we just talked about, 55.85. There's oxygen, 16. There's hydrogen. This one only has 3 sig figs, 1.01, but some periodic tables will say 1.008. Okay? So everything on the periodic table, all these numbers on the periodic table have been defined relative to carbon-12. That's how we end up with all these numbers. Could it have been different? Yes, they could have picked a different element to base everything off of. Let's say gold, the gold standard. They could have made the entire periodic table based on gold. Then all these numbers would have changed. It was decided to base the periodic table on carbon. So carbon-12 is the standard. So a logical question you might be asking right now is, well, if carbon-12 is the standard, then why does this number say 12.01? Because remember I said the way they defined it was carbon-12, and that has a mass, by definition, of 12.000 all the way out to infinity AMUs. It's exactly 12 AMUs. Yet this number on the periodic table is 12.01. So what's going on with this? Well, it turns out that in nature, there's really more than one carbon isotope that exists. There's actually 2 primary isotopes. There's other ones, but there's 2 primary isotopes. And those are carbon-12 and carbon-13. And carbon-13 does not have a mass of 13. It actually has a mass of 13.00335 AMUs. Okay? What do we know about carbon-13 compared to carbon-12? Well, we know there's actually 1 extra neutron in carbon-13 compared to carbon-12. So there's 6 protons in both of these. This one has 6 neutrons, and carbon-13 has 7 neutrons. And that bumps the mass up to 13.00335 AMUs. All right, but still, where does this 12.01 come from? Where the 12.01 comes from is each element, as determined by mass spectrometry, has a different relative abundance. So the relative abundance of carbon-12 is 98.90%. Most of the carbon-12, or most of the carbon that we find out in the universe is actually carbon-12. But a little bit of it, 1.10%, is carbon-13. There's another isotope, carbon-14, that's even a much smaller percentage, so it barely even factors into this. So how does this help us, the fact that we have two different isotopes? Well, what we need to do is we need to take a weighted average of these two things to find out what the average mass is. In other words, if we were to just start plucking out carbons, what would the mass of those averages be? So the way you do this is you take the isotope mass times the percentage in decimal form. So this would be like the isotope mass number 1 plus isotope mass number 2 times percentage in decimal form, plus iso 3, if there is one, all the way out to however many isotopes there are. So in the case of carbon-12, what we would say is, okay, the mass is 12.000 AMUs, and the percentage in the decimal form is 0.9890, plus the mass of isotope 2, carbon-13, is 13.00335 AMUs times 0.0110%. And if we add those two things together, this gives us 12.01 AMUs. Okay, that's the number that we have on the periodic table. So that is taking into account the fact that there's way more carbon-12 than there is carbon-13. So look at that, almost 99% carbon-12. So it makes sense that the average mass has got to be closer to 12 than it is to 13. There's only 1% carbon-13. That's what that bumps that little up to 12.01. So another example of how you might think about this weighted average is something like your grades in a class. Let's pretend, I'm just going to make up some numbers here, but let's just pretend that your tests are worth 75% of your grade. And let's say that your homework is worth 10% of your grade. And quizzes are worth 15% of your grade. Okay? So you've got three different contributions to your grade. You've got tests, you've got homework, and you've got quizzes. And let's pretend that after the semester is all over, your average on your test is an 83.5, your average on your homework is a 96.1, and your average on your quizzes was a 78.2. All right, so how would you actually calculate your grades? Do you just add these three things up and divide by 3? No, you can't do that. The reason why you can't do that is the tests are worth more than the homework and the quizzes. So you can't just add these up and divide by 3. You need to take a weighted average, which is that number times the percentage due to the quizzes, that number times the percentage due to the homework, that number times the percentage due to tests. So if we write out the formula for this, we would say something like 83.5 times 0.75. Remember, we use the decimal form of this, plus 96.1 times 0.10 plus 78.2 times 0.15. And if we multiply all that out and add those things together, we get 83.96. Or if we use our rules of significant figures, we should only have 2 sig figs. So that should give us an average of 84% is our final average. Okay, and you can see that's actually pretty close to the test average, which makes sense because 75% of your grade was the test average. Now, granted, I could have picked numbers that were like much lower here, which would have pulled it down, or much lower here, which would have pulled it down. But you've actually done this calculation before plenty of times yourself. You know that different things are weighted differently, and you have to take into account the weighting and your average. So all of these numbers are the weighted average of each of the isotopes times their relative abundance. That's how we end up with this number on the periodic table. So let's take a look at an example of one with 3 different isotopes, and this would be something like magnesium. So magnesium has 3 naturally occurring isotopes, magnesium-24, magnesium-25, and magnesium-26, They have relative abundances that's determined by mass spectrometry to be the following. What's the atomic mass of magnesium? So why don't you take a couple of minutes to see if you can calculate this, and we'll be back in a second. All right, and we're back. So let's take the mass of magnesium-24, which is 23.99 AMUs, and we want to multiply it by the percentage in decimal form, 0.7899, plus the mass of magnesium-25, which is 24.99 AMUs. Notice I always have to write down the units, times the percentage, which is 0.1000, plus the final isotope, magnesium-26, which is 25.98 AMUs, times the relative abundance of 0.1101. If we add all these guys up together, we get 24.31 AMUs. That would be my average mass of magnesium, and that should match up with what's on the periodic table. And indeed, that is the mass reported on the periodic table, 24.31. Now, here's the last point I want to make before we wrap up this video. If we were to go out in nature, and if we had our fancy scanning tunneling microscope and our fancy mass spectrometer, and we are measuring or determining the masses of individual atoms, what we would find is there is no such element, carbon, that has a mass of 12.01. There's no magnesium that has a mass of 24.31. This is an average over all the magnesium atoms. So if we pulled out an individual magnesium atom and were able to measure the mass, like in a mass spectrometer for instance, we would find it has one of three masses. This guy, or this guy. It's not 24.31. It's either 23.99, 24.99, or 25.98. And if we were to do this sequentially, like we were picking out one, another, what we would find out is almost 80% of the ones we picked out would be 23.99, about 10%, actually exactly 10%, would be 24.99, and about 11% would be 25.98. Okay? So just bear that in mind. This number you see on the periodic table, there is no atom that has that mass. That is the average of the abundances over all the different atoms. But if you were to pick out individual atoms, they would have whatever the individual isotope masses are. Okay, that's a good place to wrap up. The last topic we're going to hit in Chapter 3 has to do with molar mass and the mole concept, which is super important concept for the rest of the semester.